Okay, so where are we now? So we've given an overview of data science itself, and one of the things we talked about was that there's this important aspect of, data munging or manipulation, cleaning, restructuring, and so on, that is perhaps, ill-defined, but is kind of what keeps people up at night when they're working on data science problems. Okay. Then we also gave an overview of relational databases, kind of a history of relational databases and why they came into being in the first place. And we found that the original problem being addressed was this one of physical data independence, that, when aspects of the data changed, all the applications broke. And so you wanted to insulate applications from certain kinds of changes. Okay, and one of the tricks here, the secret sauce of relational databases, is this algebra of tables that allows you to reason about manipulation tasks, reason about data manipulation tasks independently of the grubby details of the physical representation. Okay. So this idea will come up over and over and over again, even outside of the context of, say, Oracle and Microsoft SQL Server and IBM DB2 and so on. You don't have to be talking about a commercial flagship relational database system to make use of this relational algebra. Okay. And we'll see that. And so I want to spend some time in this segment and probably the next few segments on understanding the relational algebra. And so, at times this may look like more of a theoretical exercise, but I promise you it's not. Right? There's an entire database course offered, say, here at the University of Washington and everywhere else that I think is a great idea to take. We're taking out segments of that are demonstrably practical in a data science setting. Okay. So I'll also mention that many of the slides in the next segment or two came from the Introduction to Data Management course developed by Dan Succio and Magda Balazinska and is taught here at the University of Washington. Okay. So the relational algebra operators that we hinted at but maybe not listed out explicitly are these. They include the set operations that are lifted to support relations, and we'll see examples of that. And then the big three are selection, projection, and join, right? And we'll talk about the meaning of those. And then there's these extended relational algebra operators that have to do with manipulating duplicates of tuples. And on the next slide, I'm going to explain where duplicates come up and why it's important to make a distinction between working when they're in the presence of duplicates and when there aren't duplicates. Okay, and these include just an operator to eliminate duplicates altogether. There's a group by operation that you may be familiar with if you worked with SQL, and this operator appears here, and then you can sort and so forth. These are extended in some. These are also extended in the sense that I shouldn't have said just duplicates. It's also sorting, for example, doesn't deal with duplicates. It's extensions of relational algebra off of away from the pure set theory-based model. So, for example, a set of objects doesn't have any kind of order applied to it, and yet we're allowed to sort things in SQL. Okay, and it's a practical, it's something that's practical for applications to be able to define what kind of order the tuples come back in, but it's not part of the formalism. It was added in afterward, and so that's this extension between the pure relational algebra and the extended relational algebra. This is probably as close to the theoretical underpinnings that I'm going to care to get. The difference between these two comes up a lot when you're trying to prove properties about the formalism, right? Because the extended relational algebra is much more difficult to prove things about if you can at all. But as a practical matter, the difference between these two classes of operators is not particularly important. Okay. So the takeaway here is that there's a big set of a rich set of operators, but if someone says the relational algebra to you, the first thing you should think of is set operations plus selection, projection, and join. Okay. All right. So this notion of sets versus bags, the duplicate question. Well, so first of all, what is a set? A set is a collection of objects where there are no duplicates, and a bag is a collection of objects where there can be duplicates. And so right up here, A is not repeated at all in a set, but it may be repeated in a bag, and whether that's legal or illegal is what gives you the semantics of a set versus bag. So you can define the relational algebra in terms of these two different semantics. You can define it in terms of set, or you can define it in terms of bag, and this notion of an extended relational algebra comes from the need to sort of work with bags, as well as other things like sorting, as I mentioned. Okay, and so the rule of thumb here, this is the last time I'm really going to mention this, the rule of thumb here is that every paper you read, if you end up reading some of the papers we talked about in this course or beyond, will, unless it's said explicitly, will assume set semantics. Okay, so be prepared for that. While every implementation, every commercial database will assume bag semantics, and we'll sort of see where that comes up in the language. Okay, so I just wanted to put that out there up front that we may play fast and loose with the difference between sets versus bags, but it can be important in practice. Okay, so one lifted set operation, you can define the union of two sets in the standard way. The union of two relations is natural, given that a relation is a set of tuples. And in relational algebra notation, I would write it like this, and I can also write it in SQL with the union keyword. And here's where set and bag will come up. If I want to, by unqualified, union does indeed remove duplicates, in which case the answer is of the union of this relation with A1B1 as a tuple and A2B1 and A1B1 and A3B4 is these three tuples. The duplicate of A1B1 didn't get passed through. To express this in bag semantics, to make sure we do include duplicates, you can say union all, and that would include all four tuples. Okay. You can define the difference operation the same way, or in the same way in the sense that you're lifting it from the set, from the natural definition of over sets, that find every tuple in this set and remove any tuples that also appear in this set. And we see A1B1, as we saw before, also appears in R1, and so you get rid of it, and all you're left with is this tuple. All right. So why isn't this one in there? Well, we don't. If A3B4 doesn't appear in R1, we know it's not in the set. All we want is everything that's in R1, removing things that also appear in R2. Okay. All right. So what about intersection? That's another set operation that we could lift up. You can indeed define intersection, but you don't necessarily need to have it as a fundamental operator because you can re-express it in terms of difference. Right? So if I want the intersection of R1 and R2, I can take everything in R1 that is not in R2, and then I can take everything in R1 that is not in that result. So if you think about this for a second, this expression returns everything that is only in R1. And then this expression overall removes everything that is only in R1, leaving things that are both in R1 and R2. And so that's what intersection is. Okay. And we'll touch on this later, but you can also express intersection in terms of join, which that operator we haven't defined yet. Okay. The selection operator is how we take tuples that satisfy a certain condition. And so we write it with sigma, and we put C to express the condition. This notation, honestly, we won't necessarily use too much throughout this course, but I think it's good to be familiar with it when it does come up. I'm more interested in recognizing the sort of English translation of these: select, union, join, and so on. The Greek notation is perhaps less important. Okay, so if we want to find where the salary is greater than 4,000 over an employee, or where the name is equal to Smith, that's an instance of a selection operator. And let's see, it says the condition C can involve equals, less than, greater than, equal to, and so on. But it can be more than this, right? It can be any sort of Boolean expression. And in fact, as we'll see in maybe a segment or two, it can be sort of any arbitrary function that returns a Boolean value. So it doesn't have to necessarily just be A less than B or A equals B. It could be some complicated function. Okay. But let's say in between some complicated function that's user defined and a simple condition like this, where you just say salary equals 4,000, or sorry, salary greater than 4,000, you can have arbitrary Boolean expressions. So you could have conjunctions. You could say where salary is greater than 4,000 and S name equals Smith. And of course you can say or and you can say not. All of these are legal. Okay. So as an example, if we want to have a selection where salary is greater than 4,000 of an employee, which ones pass this test? Well, I've been saying 4,000 this whole time, and that's 40,000. Excuse me. These numbers looked high for a moment. So John has a salary less than 40,000, and so he can be removed from the set. And so the result of this expression is this table. Right? We have tables in and tables out. The result of this expression is this table, same 3 columns, and only 2 tuples in it. Okay. I guess sometimes I gesture here, and I'm not sure you can see it when I light up. Maybe you can.